The title of this presentation is Parallel Repetition Under Anchoring: Connections with Multiplayer Quantum Games and Quantum Channels. To begin with a presentation overview, I'll be introducing some previous works from statistical physics and quantum physics, with the overall effort of serving as a motivation to begin discussing with the viewer several sources of prospective quantum advantage in information processing tasks. And just in the first presentation of the series, before I get into more details and what are actually underlying the difference in the mathematical arguments and at the same time the similarities between information processing tasks for multiplayer quantum games and also sending classical and also similarities with information processing tasks associated with sending classical bits over quantum channels, I'll be describing some previous work of myself, the author, which are relating to two-player quantum games, multiplayer quantum games, and quantum channels. And this will allow us altogether to begin describing anchoring and parallel repetition for multiplayer quantum games and to actually describe how one can basically make use of dependency breaking and view this as symmetry breaking, which is a widely discussed topic within statistical physics. And so first, like I mentioned in the overview slide, in the previous slide of this first presentation of the series, I'm interested in talking about and establishing many types of similarities between quantum physics and statistical physics. And maybe for someone, if they've seen some of my previous presentations I've been giving this year for other papers in quantum physics that I've recently posted to the archive within the past couple of months, this shouldn't come as much of a surprise because, after all, I established that there were many types of similarities, at least intuitively and mathematically speaking, for just basically making use of mathematical frameworks or physical properties of matter or phase transitions in related objects, which have really been obviously of intense interest and study for statistical physicists for decades. And how this is actually really relating to some of the aspects of quantum physics is that we can basically make use of basically similar types of frameworks or games that I've talked about in other archive preprints that I've made out this that I've put out that I've released this year, but actually making use of actually from more of a correlation standpoint and perspective. And this is relating to, as I've been mentioning on this slide, previous work in statistical physics, in which I've investigated since when I began making or putting out papers on the archive in October 2021, a lot of different types of aspects of just basically within the perspective of statistical physics, which can allow us to quantify different regimes or phases of behavior, which can also be related in of interest to explore within information processing tasks, and particularly within quantum physics. And the viewer can even see from the slide, I just put together a couple of my preprints from the archive. Pretty much 80% of my preprints on the archive now they're under submission at various journals. And they're basically relating to either correlation length lower bound for the random field Potts model, looking at logarithmic delocalization for the height function of the six vertex model, and relating that to the Ashkin-Teller generalized random cluster model and other cubic spin models, as well as even other types of related topics such as Poisson structure and integrability of a Hamiltonian flow for the inhomogeneous six vertex model, which is really looking at a way to adapt certain arguments that were used for quantum inverse scattering methods that were originally discussed for Hamiltonian systems in seminal work by Faddeev and Takhatan, in which they pretty much were talking about computing action angle variables and being able to relate that to properties of the transfer matrices and quantum monodromy matrices. And then there are even other types of preprints that I've put out on the archive, which have been relating to looking at crossing probability estimates from seminal work of Keston, in which he talked about how to basically construct an incipient infinite cluster, which basically is making use of dependence of Bernoulli percolation and basically being able to decouple scales or crossings, probabilistic crossings of the random cluster model on shorter scales in terms of longer scales, as well as even looking at an adaptation of an argument due to Dumeniu-Copan and Manulescu for quantifying or for being able to conclude that the phase transition for the Gaussian free field is sharp. And then there are even other types of basically works from statistical physics on this slide, which are even relating to parafermionic observables and other discretely holomorphic observables, which is ultimately relating to an underlying whose structure is ultimately underlined by the Cauchy-Riemann equations, as well as even eigenvectors of Toeplitz matrices, eigenvalue attraction, and phase transitions with the Seminole-Pauwels argument. So I just mentioned very briefly a lot of very general aspects of statistical physics that I've investigated in my work because overall, more or less, they all relate to basically determining whether there could be any abrupt changes of behavior in a system from from classical systems, and that's of interest in general to explore within quantum systems and being able to maybe introduce some type of decorrelation or to be able to study and quantify the ways in which quantum systems and quantum in the specific correlations that they have would actually be subject to decoherence, or how we could actually break this type of symmetry that these systems are able to that these systems inherently have and that they satisfy. And then again, now that we're talking about, and I alluded the viewer to some broad, very general themes in statistical physics, I wanted to also mention some of my previous works in quantum physics and how that's going to inform the type of synergy between statistical physics and quantum physics that I'm hoping to continue to make more apparent and discuss further throughout this new series that I've been recording. And this pretty much has to relate to the fact that we're looking at optimal and approximately optimal quantum strategies for XOR star and FFL games, which is what I studied in one work. And pretty much in that case, this is really relating to the two-player game theoretic quantum setting because it was basically me trying to expand upon some works that were given by Ostrev in which he studied XOR and CHSH games. And these are two very well-known games within quantum information theory and quantum physics and settings because it pretty much allows us to determine whether there's actually any types of effects or impacts of entanglement in which can be shared to the player's advantage so that they can achieve a higher winning probability rather than just using classical strategies and classical information alone. And these are types of points and discussions that I've made across several other videos and two previous presentations on my YouTube channel, which I'm going to kind of condense and compartmentalize for the benefit of the viewer in this first presentation of the series, which we can also relate to dependency breaking and symmetry breaking. And then in more of an algorithmic type of application and study into quantum physics, I also have this other paper, which is titled Variational Quantum Algorithm for Measurement Extraction from a Wide Variety of Partial Differential Equations. I was able to make use of and run a variational quantum algorithm for in polynomial time. And more recently this year, I've been looking at quantum games in the multiplayer setting and actually relating to that to transmitting classical bit information over quantum channels because that's relating to this first work, which is quantum strategies, error bounds, optimality, and duality gaps for multiplayer XOR XOR star, compiled XOR XOR star, and strong parallel repetition of XOR XOR star in FFL games. And then this is the second paper that's more recent from this year from a couple of weeks ago. It's relating to error correction, authentication, and false acceptance probabilities for communication over noisy quantum channels, converse upper bounds on the bit transmission rate. And so basically, this is the broad palette, I guess we could say, or broad or the repertoire of topics that I've investigated previously in quantum physics, which are going to, I hope, become more apparent to the viewer as we continue our discussion in terms of connections with dependency breaking, correlations, and symmetry breaking, and how that could relate to prospective quantum advantage. And so now I'm just going to be discussing more of the objects from the game theoretic type of setting for the first paper, optimal and approximately optimal quantum strategies for XOR star FFL games, and how this is setting the stage for not only the multiplayer setting as well as algorithmic settings that I previously investigated with variational quantum algorithms, but also how this could be of use for constructing suitable dependency breaking variables and how this relates to symmetry breaking again. So basically, the bias of a quantum game, of a two-player quantum game beta, is given by beta of G of script S, where script S denotes the set of all possible strategies, which is given by a summation over little s and little t, where these two variables respectively denote the questions are distributed to each of the two players from the referee's probability distribution, which are belonging respectively to big S and big T. And we're taking the summation over this expectation of G of ST, namely the game matrix G, as well as a mixed quantum state, which is given by a bra of the optimal strategy for playing the game using quantum strategies and quantum information, bra psi, as well as the tensor product of these two quantities, A sub s and B of t, which respectively represent the tensors that each one of these players construct when they're responding to questions little s and little t drawn from the referee's probability distribution, where A and B denote Alice and Bob, which are the two archetypical type of players, which everyone always talks about as and refers to as participants in quantum games and basically other types of information processing tasks that are of great interest in our of interest for seminal work and discussion in quantum information theory, as well as KET-Psi. So this is the bias of the game, which is going to actually be used, as I'll demonstrate to the viewer, can basically be employed to discuss notions of optimality, duality gaps, and error bounds, which are of great interest in use in dependency breaking type of arguments. And the question sets for the two-player games, as we had alluded to, can explicitly be written out as A sub big of S and B sub big of T, where each one of these question sets can be identically expressed as a union over little s and big S, as well as little t and big T of A of S and B of T respectively, which is given by the collection of little s and big S, where A of S is either +1 or minus one, as well as for Bob's tensor of answers, the collection of little t and big T, such that B of T is either +1 or -1. And generally speaking, when we're looking at quantum information theory and quantum games, we're interested in looking at binary valued variables because, after all, when two players such as Alice and Bob, they're participating in this game, like I've been describing for the viewer, and responding to the questions drawn from the referee's probability distribution in order to win the game or to satisfy the referee's predicate or their scoring predicate that they're going to use for determining whether the responses from Alice and Bob satisfy, say, some XOR formula or some other type of formula that one could make up. You're looking at whether it's either satisfying yes, corresponding to the answer or the entry from the player observable from Alice and Bob being -1, or conversely, or opposite, or in the contradictory sense, whether that type of same entry or response from Alice or Bob would be a +1, hence constituting a winning strategy and a response that can be used towards satisfying some formula for the referee's scoring predicate. And a linear relationship, in fact, between the bias and the optimal value for a game that's given for even two-player game or a multiplayer quantum game is given by the bias beta sub g of s, which we had introduced 2 slides ago, as just basically being a summation over expectation values where the bra and ket states are given by quantum states corresponding to the optimal strategy that Alice and Bob can use for playing the game, is given by 2 of omega of g of s -1, where omega of g of s is the optimal value of the game. And so the optimal value of the game is a central object that's very important for information theorists or even people who may not study quantum games or look to use quantum information, is important because it's just classified and defined directly, explicitly as the maximum probability, namely the supremum of all types of probabilities that the players Alice and Bob can use, or even groups of an arbitrary number of players in the multiplayer setting, which can be used for winning the game and satisfying, again, like I had mentioned and alluded to the viewer or drawn the attention's viewer to in terms of the referee's scoring predicate. And we can majorize the bias, which is allowing us to remove the dependency of the set of all strategies script S by taking the supremum over script S, which is looking at the maximum bias, beta sub G. And in general, we're really looking to formulate and to phrase optimization problems for several types of information processing tasks that are that are of interest to study either for two-player quantum games or multiplayer quantum games altogether, because this is allowing us to determine what's the best or worst case scenario in which someone could actually hope to make use of quantum advantage for some type of perceived benefit so that there can be some type of prospective quantum advantage. And in general, as it shouldn't come as a surprise, from those other types of previous works in quantum information theory that I provided for the viewer and briefly described and motivated in an earlier slide, optimization and in particular semi-definite programs and constraint optimization problems are of great use and great importance in coming to play at several other types of perspectives or several other types of points of our study of quantum information theory, because it can allow us to determine whether there's actually some type of perspective advantage or some type of superiority of quantum information as far as information processing tasks goes that would allow us to increase the probability using quantum information and entanglement in comparison to classical information. And this is really coming into play in terms of why, historically speaking, foundationally speaking, from the from the very beginning of quantum mechanics, why EPR pairs and entanglement, they're coming into such of a play. And even in Einstein's discussions and his thoughts and interest in quantum mechanics and trying to determine whether it's actually a viable in a viable and a very an inaccurate theory of nature, and how this actually relates to how entanglement can be manipulated and further made use of by players, Alice and Bob, or even arbitrarily number of players in multiplayer quantum settings that we're going to be further describing. And the epsilon approximality of the bias is also helpful because, after all, if we're going to make use of semi-definite programs or constraint optimization problems for determining when things or when the strategy of a quantum player or his or her behavior is the most optimal, we can look at epsilon approximality, namely fixing some strictly small parameter epsilon and looking at whether some type of inequality of this form would hold, namely beta sub g of s, namely the bias independently of taking the supremum or before we take the supremum is upper bounded by obviously the supremum of overall strategies beta sub g, so namely the bias that's independent of the strategy script s, as well as being lower bounded by a 1 minus epsilon multiplicative factor of the bias independent, which again is also independent of the set of all possible strategy script s. And this is really allowing us to, again, determine whether there are deviations or whether there are maybe some questions maybe within the referee's probability distribution that Alice or Bob or countably many number of players could have responded to, which could have actually been maybe answered in a different type of way, which could have increased their probability for being able to win some game by making use of quantum strategies and hence also by making use of quantum information. And we can formulate the optimal value of the two-player game through a constraint optimization problem. Again, this shouldn't come as a surprise given the type of discussion and the type of motivation that I've been attempting to lay out for the viewer over the past couple of slides, in which, in this particular instance, we're looking at a constraint optimization problem over A sub I, B sub jk, and psi, namely the tensors of possible responses that Alice can form and Bob, and that Bob can also form in addition to psi, namely the strategy, the quantum strategy that they can make use of. And this is given by the fact that we're looking at a 1 over 4 normalized by a combinatorial factor, little n choose 2, where little n represents the total number of questions from the referee's probability distribution that are being distributed to Alice and Bob, the two players of the game, as well as a summation over one between one and the total number of questions little n from the referee's probability distribution of little I and j, where little I and j are indexing the tensors which are appearing in the intermediate term of this expectation value that we're taking the supremum over. So basically, this type of expression is very important and it's very informative for actually formulating the optimal value of a game using quantum strategies, because we're looking at some type of superposition of tensors corresponding to the responses of each player, of each participant, and determining whether this would actually have a positive or negative effect towards increasing the supremum of the winning probability that we would like to maximize. And this is given by the fact that we have some terms a sub I and B sub ij, as well as a sub j and B sub ij, as well as a sub I, B sub ji corresponding to the third term. But there's a last term within this supremum that we're within this expectation value that we're taking the supremum over, which is actually having a minus sign, which is, if you'd like, an anti-commuting term, which is reflecting the fact that given the prospective quantum advantage of XOR games or other two-player games, in the specific instance of the XOR game, the maximum winning probability is 75% using classical strategies, but 85, 86%, if I remember correctly, or like 10 or 11% more using quantum strategies, which is overall reflecting the types of responses which can be drawn, which can be constructed from Alice and Bob's responses to some questions drawn for the referee's probability distribution, for which, unfortunately, they would lose the game and not satisfy the referee's scoring predicate. In this type of expression for a constraint optimization problem, it's extremely helpful because in one of my more recent papers that I put the first version out of in May this year, I pretty much was looking at how to formulate and extend and be able to expand upon this type of very simple expression for the optimal value towards constructing towards constructing semi-definite programs as well as dual semi-definite programs and dual objective functions, as well as being able to posit upon and construct error bounds, which can be of interest towards determining how much would the maximum probability for winning a game using quantum strategies decrease under certain assumptions and certain circumstances that the players could find themselves in when they're responding to questions drawn from the referee's probability distribution. And the outer products from the responses of each one of the players are placed into correspondence with the following tensor representations. So again, this is to say that we have these outer products, which are given on the left-hand side of this column here, the left-hand side column on the slide, as well as we have these other tensor product or these tensor product representations, or sorry, these tensor representations, product of tensor representations, in fact, which are corresponding to the possible set of responses that Alice and Bob can reply to or can provide in response to the referee's probability to questions drawn from the referee's probability distribution, which are indexed in little I and little j. And this is just again to draw the attention of the viewers fact that the anti-commuting outer product, or namely the outer product within the superposition that was given in the previous slide for the optimal value as a constraint optimization problem, it's really coming into the fact that it can be expressed in terms of an outer product with ket j and broad j. And as well, this is again, can at least be of interest already to the viewer because it's something that I made use of for actually being able to analyze multiplayer optimality and duality gaps from these type of expressions and being able to formulate optimal values from basically collections of commuting and anti-commuting terms, namely terms which either have the same sign or have a minus, to determine which types of possible strategies within a potentially a very large, maybe even potentially infinitely large combinatorial space could be analyzed within the perspective of quantum information theory for determining whether prospective quantum advantage exists. And again, given that in a previous slide we had defined epsilon approximality of the bias, it shouldn't at all come as a surprise to the viewer that we can also describe and be able to formulate epsilon approximality of the optimal value. And this is given by the fact that for the XOR game has an optimal value that's 1 over square root of 2. And it's a nice little expression, which is actually helpful for determining whether one can actually be able to formulate some type of very similar, simple, or closely related type of expression for parallel repetition of the game. And basically, parallel repetition is relating to conducting independent rounds of a game in parallel or sequentially, one after the other. And this is given by the fact that, again, given the existence of another potentially small, strictly positive parameter epsilon corresponding to the optimal value, we can characterize epsilon approximality or near approximality of the optimal value of the game by taking the same supremum that I had given in a previous slide for the optimal value and upper bounding it by 1 over square root of 2, because overall the fact that for the XOR game, 1 over square root of 2 represents the optimal value of the game, hence the maximum probability of winning the game. At the best case or the best instance, using quantum information, the winning probability of Alice and Bob would be equal to this value. But epsilon approximality or near approximality of the optimal value would also stipulate that as a lower bound, we can have, again, a multiplicative factor of 1 minus epsilon times 1 over square root of 2, namely the maximum winning probability, but being able to quantify some deviation from epsilon through the 1 minus epsilon multiplicative factor from the optimal quantum strategy that Alice and Bob can use. In the semi-definite program, SDP formulation is something that I've discussed in other types of presentations and videos that I've given on the channel. And again, it's coming into play from the sense that it's a different type of optimization problem, but it's still something that's extremely important for allowing us to be able to quantify and to be able to determine basically various types of ways that we can study error bounds or seek to generalize error bounds for multiplayer game theoretic quantum settings. And this is given by the fact that, again, the objective that we're looking to take this constrained supremum over with the semi-definite program formulation is given by an inner product of the game matrix G with the primal feasible solution, which is given by Z, as well as given by the fact that the constraints that we're placing on the primal feasible solution for the game through this SDP formulation is given by the fact that we're taking the ordering of Z with respect to the ordering of the partial semi-definite cone in stipulating or demanding in our constraints for this optimization problem that's strictly positive, as well as given the fact that we're also stipulating that for all I between 1 and m, the another objective f sub I times the primal feasible solution is identically equal to c sub I. And it shouldn't come as a surprise that why a lot of people like to make use of semi-definite programs and why it's been of such broad use and broad applicability through several information processing tasks within the field of quantum information theory and quantum information processing is that it's relating to the fact that we can formulate a dual program, namely a dual SDP formulation. And this is basically relating to the fact that we can formulate a dual SDP or a dual semi-definite program from the original semi-definite program by taking the supremum to an infimum or vice versa, an infimum to a supremum, and interchanging the place of the objective the objective, which in the case that we gave in the previous slide in the present of this presentation was given as being dependent upon the primal feasible solution Z to the game, as well as also introducing a new dual objective function in, pretty much also, as we mentioned, interchanging and modifying the constraints over which we would like to take the optimization problem. And so basically having this in mind is also distinguishing the semi-definite programs a little bit from the constraint optimization problems and programs that I'd given for expressions of the optimal value, because it's basically allowing us to actually make use of the dual formulation of this program of this problem so that we can actually be able to make use of this type of information for studying primal feasible solutions for a wide variety of games. And the dual gap SDP formulation is really encapsulating and relating to the fact as to whether there can actually be prospective quantum advantage for a game in the first place. Because after all, if one looks up a lot of talks from very prominent researchers, it's always never a given in terms of whether quantum information processing or quantum algorithms can actually impart some type of advantage. And I think that unfortunately that's maybe one I guess I would say it's one downfall of the quantum computing industry, because it's really unfortunately at times presenting a lot of unrealistic expectations for the field, because there's not always a quantum advantage or perceived prospective quantum advantage for every problem. In fact, there are many problems where it's better to use classical computing after all. And this type of inequality is really encapsulating that fact, because we can look at the dual objective, which is given by f sub I, which is multiplied by y sub I, and subtracting it from the game matrix. and multiplying by the primal feasible solution to some game of interest and determining whether that is greater than or equal to zero. So obviously, if this type of difference between the dual objective and the game matrix when being multiplied or taken the inner product of with the primal feasible solution, it is positive, there would indicate that yes, there are some aspects of entanglement in quantum information that could be useful to actually allow some players to gain some perspective quantum advantage, which is more of the best case scenario that we would probably want to further investigate. And again, now that we've been talking about and discussing the two-player game theoretic setting, I wanted to move over to the multiplayer game theoretic setting, which is again the subject of work of from this recent preprint that I put out on the archive earlier this year for quantum strategies, error bounds, optimality, and duality gaps. And again, it's going to just relate to, again, in many cases, being able to generalize the expression for the bias that I'd given in the two-player setting and how this is actually relating to more complicated expressions for bias and how this can actually be used to characterize optimality. And again, we can just start by looking at what is the set of all player tensor observables for the 3 XOR game because it's the most simple type of multiplayer quantum game beyond the two-player setting, namely adding one more player, which we can denote as Clio, and then pretty much looking at the tensor product or the space of all player tensor observables, namely the space of all possible combinations of responses that Alice, Bob, and Clio can prepare to questions drawn from the referee's probability distribution uniformly at random. And the multiplayer bias, as one would not be surprised for and could expect, is given by the fact that it can also be used to satisfy and to be able to characterize optimality because there's basically a very similar type of expression for optimality of the bias, namely there's some 1 minus epsilon multiplicative factor, which is given by the bias, and this is being upper bounded by a summation over the number of questions of mixed quantum states or expectation values, which are given by Braz in the optimal strategy and Ketz in the optimal strategy, as well as the intermediate term to the summation of expectation values being dependent upon a tensor product for the tensor of all possible player observables, where the number of terms that we're including in this tensor product is indexed in the total number of players or participants in the game, which in this case we've been discussing as 3, but it can be used for multiple players, arbitrary number of players, an arbitrary number of players, in fact. And this is, of course, as one should not be surprised, being less than or equal to upper bounded by just the bias of the game in the absence of the 1 minus epsilon multiplicative factor. In parallel repetition of semi-definite programs is coming into play because we can pretty much take the semi-definite program that we had given in the previous slide and being able to formulate a parallel repetition version of it, namely taking the game matrix and performing some parallel repetition operation to it as given as the first component of the objective in this semi-definite program, as well as also performing parallel repetition on the primal feasible solution for the game, which is, again, as one should not be surprised, given by the fact that we're still enforcing constraints on the primal feasible solution, in fact, parallel repetition of the primal feasible solution for the semi-definite program with respect to the partial ordering of the positive semi-definite cone, given the fact that we're also making sure that the dual objective multiplied by the inner product between the dual objective and the primal feasible solution is identically equal to some collection of real constants. And equivalently, parallel repetition of semi-definite programs can be formulated with primal feasible solutions in game matrices of game theoretic settings and multiplayer settings before the parallel repetition operation is performed, namely taking the same type of construction for the semi-definite program that we had given it in the previous slide in performing the wedge operation or the parallel repetition operation across however many rounds of parallel repetition we're executing for the game of interest. In parallel repetition of the primal feasible solution satisfies the following decomposition, namely the primal feasible solution associated with parallel repetition of the XOR game as one example of a two-player game and multiplayer game that someone can analyze and study from the perspective of parallel repetition and optimality and duality gaps and these types of related objects that we've been discussing through semi-definite programs and constrained optimization programs can be identically decomposed as the strong parallel repetition operation, where the index J, which is appearing in the top part in the subscript of the primal feasible solution corresponding to the XOR game, is given by ranging over little one, or sorry, a one in a little n, so namely little n rounds of parallel repetition. And parallel repetition of dual semi-definite programs can be formulated in an intuitive type of way, in a very clear type of way, given the types of settings that we've been discussing for dual semi-definite programs and dual SDPs for the two-player setting, namely that we're performing this wedge operation corresponding to parallel repetition in front of an infimum corresponding to the fact that the correspondence between an original semi-definite program and the dual semi-definite program is given that we're interchanging the order of the constraints as well as changing a supremum term to an infimum, or an infimum to a supremum, as well as given by the fact that I introduced some different type of notation for this dual objective function, given the fact that we're taking a summation over parallel repetition of each one of the question sets for each one of the players, which is what the dual objective function is indexed in. And also related to parallel repetition of semi-definite programs and dual semi-definite programs, there's also another important fact that we should keep into mind, namely the fact that parallel repetition of the game matrices for either a two-player game or a multiplayer game satisfies the following decomposition. Namely, we can formulate and be able to study a more complicated object, namely a symmetrized game matrix or game tensor for parallel repetition of the XOR game or other types of games, which is given by the fact that, again, shouldn't come as a surprise that this type of symmetrized game tensor or game matrix, depending upon the specific game that we're considering, can be identically be expressed as terms of the wedge operation, again, over the little j index, which is appearing in the subscript of the symmetrized game tensor for the XOR game, which can identically be expressed in terms of the parallel repetition operation performed on this matrix representation, which is given as having zeros on the diagonal, as well as the conjugate transpose of the game matrix in the first term of the anti-diagonal, as well as just the game matrix itself along the remaining element along the anti-diagonal, which can be identically expressed in terms of just still zeros along the diagonal, but the parallel repetition operation applied to each one of the representations or each one of the blocks along the anti-diagonal of this game, of this higher dimensional game matrix that we've been constructing, that we're taking the parallel repetition operation of. In other recent works that I've been describing and been motivating for the viewer on quantum information theory and quantum physics for this year, that are mine, that I've been writing and thinking about, continue to demonstrate how multiplayer game theoretic settings are also of importance to cryptography. And this is really relating to the fact that I was drawing the attention to the viewer to the fact that there are some types of instances and aspects of quantum channels that can actually be helpful for us to describe and think about, which can help us get into mind and get into the framework and the mindset of actually looking at dependency breaking variables and breaking down correlations and determining how that would affect prospective quantum advantage. And this is again given by my other paper that I put out on the archive a couple of weeks ago that I made a presentation in another series for, which was titled Error Correction, Authentication, and False Acceptance Probabilities for Communication over Noisy Quantum Channels. And pretty much this type of paper is relating to the fact that you can think about it as relating to the following two parameters. Because overall, we know that quantum mechanics, it's really shocking or it's really counterintuitive or paradoxical in comparison to classical physics, because it's basically claiming at one of its most fundamental levels that due to the Heisenberg uncertainty principle that we can't be able to observe with ultimate precision or the highest probability as possible the position and the momentum of these two of a physical system simultaneously. And this is resulting into the fact that due to the Heisenberg uncertainty principle, we look at the fundamental constant, the Planck's constant h bar, resulting in constituting a lower bound or part of a lower bound for the product of the momentum and the position of some physical system. And this is really manifesting in terms of information processing tasks in terms of quantum channels, because we can introduce, again, like I've been mentioning to the viewer, the following two parameters for the noise level over the quantum channel between Alice and Bob, as well as the noise over the quantum channel between Bob and Eve, which is given by N and the A between the arrow between A and B, as well as N corresponding to the noise level also for also Bob and Eve channel, which is also given by the arrow between B and E. In a paradoxical assumption, which shouldn't come as a surprise because we're talking about quantum physics and quantum information processing and quantum information theory after all, with regards to noise levels of each quantum channel relates to the following, namely that Alice and Bob can actually achieve some type of prospective quantum advantage for information processing tasks that can be associated and formulated with the transmission of classical bit codewords and classical information over quantum channels, in spite of the fact that the noise over Alice and Bob's channel dominates the noise over Bob and Eve's channel. So obviously, I'm not going to be able to get into the all the nitty gritty, so to speak, or all the details in terms of why the prospective quantum advantage holds given this paradoxical assumption that Alice and Bob have more noise over their quantum channel. It's in the other presentation on the channel on my YouTube channel. I kind of break down parts of it here and there, but it's basically relating to the fact that there can be some type of generalization of a very suitable function that Alice and Bob can use for maintaining their prospective quantum advantage so that they can minimize the probability that Eve can try to tamper with or try to corrupt their information that they're transmitting to the other player through classical information and classical bit codewords over the quantum channel. And the expression for the bit transmission rate, which we denote with R, is given in terms of the mutual information and the conditional Shannon entropies. And this is basically relating to the fact that when we're talking about information, and whether it's classical or quantum, and it's being distributed over or it's being transmitted over some quantum channel, which the other player is hoping to be able to decode from some other player's encoding with some good probability, we're pretty much looking at expressions for the bit transmission rate R, which is given by a supremum over probability measures P sub x, where this boldface x term that appears as a support on the probability measure that we're taking the supremum over, it's given the fact that we're looking at the support for different types of classical bit codewords that Alice and Bob can transmit over the quantum channel. And the supremum term is given by first a minimum of the conditional mutual, or sorry, a minimum of the mutual information entropy, which is given by I of boldface x and boldface y, namely the mutual information between two random variables, as well as also the minimum, which is appearing in terms of a minimum over a conditional Shannon entropy given this little z term, which, as I've been discussing and describing in other presentations on my YouTube channel, in another series, it's given by the letters which Eve, as the interceptor, can introduce into the quantum channel to try to prevent Alice and Bob from being able to make use of quantum information aspects of quantum aspects of information for being able to maintain prospective advantage. And the converse result on the bit transmission rate, which I studied, is relating to the fact as to whether an inequality with the reverse direction holds. Namely, we're still looking at a supremum over probability measures as well as a minimum between the mutual information entropy and the difference between these conditional Shannon entropies, but whether the inequality could point in the other direction, which actually has wide-reaching and important and significant information processing consequences. And this is related to the bit transmission rate, also are the error correction and authentication probabilities, because this is, after all, relating to the fact that error correction as a fundamental aspect of quantum information theory, it's allowing us to maintain prospective quantum advantage by basically being able to determine whether there are any types of ways in which we can anticipate how errors in quantum systems would arise and how we can correct for those errors. As well, also, there's an authentication probability, which is given by the probability of Alice and Bob being able to just basically authenticate with good probability any type of information that is distributed and transmitted and ultimately encoded by another player or another participant through classical bit code words and classical bit information over the quantum channel. And such probabilities are denoted as follows, namely, in a lot of other presentations that I've given on the channel, I've made use of these types of, this type of shorthand notation because it's really helpful for just being able to compare error correction and authentication probabilities for the channels either between Alice and Bob or Bob and Eve, and how they actually relate to potential potential avenues or potential opportunities for prospective quantum advantage. And for code words with infinitely many bits, computations with probabilities introduced in previous slides take the following form. Namely, we have been introducing and also describing how the probability of error correction can arise within either a more algorithmic sense for quantum algorithms or even other types of more theoretical information processing tasks, and how this is actually relating to the probability of error correction over Alice and Bob's quantum channel for code words with infinitely many bits is given by the limit as the number of bits little n of the code words approaches positive infinity, given by a union over all instances of error correcting codes, such that the probability that Alice and Bob implement an n-bit error correcting code literally c over the quantum channel between them, between Alice and Bob A and B, as well as obviously intuitively one can anticipate how the probability of error correction can similarly be formulated for code words with infinitely many bits over Bob and Eve's quantum channel. And the overlap function between the alphabets of Alice, Bob, and Eve generalizes the prospective quantum advantage for code words with infinitely many bits. Namely, given the alphabets, or given the collection of random variables which we can use for the alphabets for Alice, Bob, and Eve, given by respectively by boldface X, boldface Y, and boldface Z, we can determine whether there's some C star, some strictly positive parameter, such that if the overlap function, or namely the total number of letters that are in common between each one of the alphabets between Alice, Bob, and Eve, the three participants in this information processing task, whether it's identically being equal to C star would mean that this holds if and only if the noise over Alice and Bob's quantum channel is larger than the noise over Bob and Eve's quantum channel, or otherwise, if the threshold is greater than C star, prospective quantum advantage would hold if and only if the noise over Bob and Eve's quantum channel is greater than the noise between over Alice and Bob's quantum channel. And now I'm going to describe more of the dependency breaking perspective and the connections with statistical physics that I've been providing and discussing for the viewer earlier in this presentation. Namely, the fact that this is the title of the paper that I'm probably going to be putting out on the archive soon. This is the title that I have in mind right now. I might change it, but this is probably the title that I'm going to use, which is relating to parallel repetition of expanded and multiplayer quantum gains, anchoring, optimal values, generalized error bounds, dependency breaking, asymmetry breaking. So this is encapsulating and putting together all these types of results that I was thinking about, namely the optimal value and how that relates to an optimization program and the formulation of semi-definite programs and dual semi-definite programs, as well as how it's relating to error bounds and different types of ways in which one could hope to generalize error bounds, and as well as finally dependency breaking, asymmetry breaking, and how this can actually be achieved in terms of anchoring. And I haven't described anchoring, but don't worry, I'll describe it in the next presentation or so. But it's just basically a potential theoretical approach in a way to just basically remove correlations from a quantum system. And the product of question sets for each one of the players is given by this type of expression, namely, we're looking at a product over some Q sub I, which is representing the questions which are distributed to each one of the players from the referee's probability distribution, as well as each one of their respective answers, which is given by the A sub I. And the referee scoring predicate, which we have been talking about, which is of use in both two-player settings and multiplayer game theoretic settings, is given by the predicate P, which is a function of each one of the questions little q sub I, which are distributed to each one of the players countably many number of questions from the referee's probability distribution, as well as the predicate, which is V, which is a function of the answers as well as the questions that are distributed to each player from the referee's probability distribution. And the parallel repetition of question sets is given by the fact that we can look at the tensor product of the q sub I, the script q sub I, which is given in a different font than the previous question sets, which were given earlier, because it's indicating that these are the types of question sets that we're going to be looking at for the purposes of anchoring. And this is given by the fact that we can raise this question set to the tensor product of k, of little k, which is given by the fact that this is the collection of all questions where we're looking at collections of tuples for each one of the question sets which are distributed to each player for each repetition, each parallel repetition, or each instance, each independent instance of the game that we're repeating to determine what is their prospective quantum advantage or how would the maximum probability for winning the game differ. And the parallel repetition of the XOR optimal value is given by the fact that it's different from the optimal value of parallel repetition of the optimal value for the FFL game, because this optimal value is actually equal to 1/2. So actually the optimal value under one round of parallel repetition is given by equaling 1/2 and not equal to 1 over square root of 2, which is the value that I'd provided and discussed earlier for the viewer in this presentation in the series. But on the other hand, just because parallel repetition changes the optimal value for one game, it doesn't mean that it changes it for all two-player games. And this is given by the fact that there's an invariance principle or a statement of invariance, a parallel repetition for the optimal value of the FFL game, which is given by the fact that parallel repetition of the FFL game leaves the optimal value or the maximum winning probability invariant or equal, namely the fact that before and after performing the parallel repetition operation, the optimal value is equal to 2/3, which is not equal to the square of 2/3. And this is relating to, again, some types of results, which I just wanted to provide at the end of this first presentation of this series, but that I haven't defined all these objects are, just to give the viewer a kind of brief taste and a brief impression of the types of things that we can actually make use of and that we can actually study, making use of parallel repetition, as well as being able to make use of dependency breaking variables for removing quantum correlations. And this is given by the fact that it's relating to the following three complexity-related results. Big O notation is often used in complexity theory because it's just basically describing what is a best algorithmic type of estimate or guarantee for being able to, in this case, achieve and maintain some type of prospective quantum advantage as far as information processing goes. And this is given by the fact that the three main results, which I'm going to focus on and more and discuss, which are relating to computational complexity, are relating to the fact that we're looking at providing these three big O results, which are looking at just basically ratios of various ratios of constants that we can define for multiplayer games, as well as the multiplayer anchoring probability, which are then allowing us to determine or to conclude that there's some type of rate of decay of the optimal value of a parallel repetition of a game as we're performing anchoring. So this is just basically some type of very brief, again, overview or view or vista, I guess we could say, or perspective, whatever you want to call it, of just basically the type of upper bounds that we're going to make use of for actually looking at, basically being able to upper bound a system of expectation values, as well as a system of positive operated value measurements, which is actually, as I'll describe for the viewer in other presentation of this series, directly bridging the gap between probability and quantum mechanics, because it's making use of trace of tensor product representations and being able to define those as probabilities through positive operator valued measurements, and how actually one of the main results, which is having some implication in terms of the decay of the optimal value of the game under anchored parallel repetition, is relating to directly establishing a comparison in a perspective between quantum mechanics and probability theory. And then as the third result, we're making use of some upper bounds with Pinsker's inequality, which is making use of just basically the fact that the L1 norm between two quantum states is upper bounded by the relative entropy. So it's, again, just demonstrating how entropy, how it also comes into play for information processing tasks for classical bit information and classical bit cohorts over quantum channels. It's also coming into play for some of these complexity related results I'm going to be describing further for the viewer later in other presentations of this series. Okay, and so the conclusion that I wanted to end out with was that we were introducing previous works from statistical physics and quantum physics and establishing several types of connections. And we were introducing the bias and optimal value, parallel repetition, SDPs, and dual SDPs and several related objects. And this was allowing us to introduce some types of statements through complexity related results for anchor parallel repetition. And thanks for watching.